All right, so let's discuss this problem out of boundary paths. Okay, so what does this problem states? Let's go to the problem. There is a m cross n grid with a ball. The ball is initially at a position start row and start column, and start row and start column, they are one indexed, right? Zero indexed, and the ball can move to four adjacent cells of the grid, and we can apply at most max moves. What is the aim? The aim is to move the ball out of the boundary of the grid. Okay, as you can see over here, if I move upwards, the ball comes out of the boundary of the grid. Okay, like over here, if I move by one position, I come out of the boundary. Over here, if I make two moves, once I go down and I go left, I come out of the boundary of the grid, right? And over here, if I come down and again if I make a move downwards, I come out of the boundary of the grid. Over here, as you can see, if I go to the right and if I go upwards, I move out of the grid, right? So the maximum number of moves is 2, so that's why we are considering for one move at a time and two moves at a time. Okay, so I hope the solution is sorry, the problem is clear, and let's try and understand the solution and build an intuition so that we can code the problem, right? So all right, so we have been given a grid, right? Let's say if it is a 2 cross 2 grid. Initially the ball is over here, right? So we want to find out those paths that can take the ball out of the boundary, out of the boundary in at most say 2 moves. Okay, and initially the ball is at 0 comma 0. So let's see, right? Now to realize like what this problem asks us to do, let's do a basic dry run. Okay, so let's say if I want to try out the possibilities where I make one move and I reach out of the boundary. Okay, so if I make one move, I go to this cell. If I make one move upwards, I go out over here. If I make one move to the left, if I come down, I make one move. But in these two cases, I don't go out of the boundary, and I go out of the boundary in these two cases. So I write 2 as an answer. For one move that I make, I can go out of the boundary. All right, I hope I'm clear. Now, okay, stroke eraser. Now let's see. Say if I can make two moves, I want to know what are those paths where I make two moves and after two moves I get out of the boundary of the grid. Okay, so if I come down over here, then from here if I go left and if I go down, I come out of the boundary. I can also go right and also I can go back as well. Okay, so this is not your typical DFS where you mark the previous state as visited in order to keep a track of the visited states so that we don't visit it again. The question does not demand that approach. Okay, so I'll come to that case once I discuss another test case. Okay, so now over here you can see if I make a move down, I can make these two moves to come out. So I'll make 2 over here. Let's say if I move to right, okay, then I can move up, I can move right, I can move down, I can move left. So these two moves, they don't add up anything, but these two moves, they take me out of the boundary of the grid. Okay, similarly, we cannot move this way, right? So we have covered all the test cases, right? All the possible cases that we can make. So I hope I'm clear on this. Okay, let's discuss another test case. Let's say I have a 3 cross 1 grid, sorry, 1 cross 3 grid. Okay, now let's say initially the ball is here. Okay, and what is the maximum number of moves that I can make? I can make 3 moves. Okay, let's say, let me just explain what I meant by when I said that we can, go back to the state that we have already visited. Let's say if I can make three moves and I want to consider all the possibilities or the paths that take the ball out of the boundary of the grid after making three moves. So let's say if I come over here, I make one move, I go back at this place, I make one move, and I can take an exit. So this adds up to 2. Similarly, I can move to the right, I can go back, up and down. So 2 moves. As you can see, I'm clearly making 3 moves for these 4 paths, and all these paths are unique. Okay, so let's try and understand the intuition. Okay, all right, let's consider our test case. Okay, at most 2 moves to make. All right, I can make either one move, I can make 2 moves, and I want to find out all the possibilities, all the paths that take the ball out of the boundary. Okay, let's be quick this time. So as you guys can see, we have options. Okay, let's say if I know the answer, if I want to know the answer for this cell. Okay, we are let me just go once again. Let's say we want to find out all the possibilities, right? And we can move in either directions. I can move to the right, I can move upwards, I can move to the left, I can move downwards. So this is your typical DFS question, right? Wherein you have been given a grid, and in that grid you can make 4 moves. You can either go up, down, left, right. So these type of questions, they are very famous, and they actually involve the recursive thinking or the recursive approach to solve the question. So let's see how are we going to analyze and make a mind map of how to solve this type of question once we get this. Okay, so as you can see, I can move to 4 directions. I can either move up, left, right and down. So there is a clear indication of choices for a given set of inputs, okay. So this triggers the intuition that I might be tempted to opt recursive solution, or I might try a recursive approach, okay, to solve this question. Okay, so why recursive approach, or how will the recursive approach work? We'll come to that later, but for now let's try and realize why have we adopted recursive method. It is because, let's say if I want to know the answer for this state. Okay, what is this state actually? We have the start row as 0, we have the start column as 0, and the number of moves that I can make is 2. Okay, this has been given to us. All right, if I want to know the answer for this state, what does recursion say? Find the answer for one case and I'll get you the answer for the remaining. Okay, so by chance, if I jump to this cell, what will this state be represented? What will be the parameters that represent this state? This is 0th cell, this is first, this is 0, this is 1. So the row number is 0, column number is 1, and now that I have made one move, the number of moves will be 1. Okay, so if I know answer for this state, if I know answer for this state, what will be this state? This state will be 1, 0 and 1. If I know answer for these states, okay, if I know answer for these two states, and also for this will be a base case, right? Because when I come out of the boundary, I return 1. Okay, I have gotten a path that takes one move and takes the ball out of the boundary. All right, so all these 4 possibilities, once I have the answer for all these 4 possibilities, I can calculate the answer for the current cell. How can I calculate the answer for the current cell? I can simply add them up. I can add these answers, right? This is the magic of recursive thinking, that if I have the solution for remaining cases, I can frame the solution for current case. Or we can say it otherwise, that if I have the solution, or if I want to find the solution for the current cell, I will solve it for this one and I'll ask recursion to solve it for the remaining cells. Okay, as simple as that. So let's do a dry run. Okay, now let's say initially we are at start position, that is 0, and another column number is 0, and we can make at most 2 moves. All right, so what are the 4 possibilities? Okay, let's say if I come downwards, the column will remain same. I have already made one move. Or the other case might be I might go up. So row number might decrease, column number remains same, the number of moves becomes 1. What might be the another case? Another case may be I remain at the same row, but the column number decreases and the number of moves also decreases, right? Now let's see. Okay, so let me just side by side, let me just draw the situation as well. Okay, this question is pretty good if you want to get a clear understanding of how recursive thinking works and how DFS works. Okay, so the ball is over here currently, right? We have two moves. Now for this one, if you can draw the diagram for other states, that will be good, or else you can watch me draw. Okay, so does this state? The column has decreased, okay, and the row number remains same. So ball was initially here, the ball will come out, and this is what we wanted. Okay, now over here for this one, the ball is over here, right? And for this one, where does the ball go? The ball increments, sorry, the row increments, so the ball comes here, right? So now the states have updated. Now for this case, okay, what do? We make 4 calls, right? We make 4 more calls. Okay, what will this call be? This call will be for decrementing the row. Okay, so let's say if I do a -1 in my row, that means if I want to make an upward move, I'll make this 0, this will also be 0, and I have made all the moves, so the number of moves will also be 0. All right, so this one corresponds to this state, right? This state. Okay, so the way we came down, the same way we went up. Okay, am I clear? All right, or let me just erase this. I actually considered incrementing it for this current state, so we'll also follow the same pattern. So let me just erase this, and let's say if uh, if I increment it, okay, if I increment my row, this is the row, so let's say if I jump out of this, so if I increment it by 1, I will go to this row. Okay, so now the state will be this. Okay, so this is our favorable case. What do? After this, we don't call for any further states, because we have reached to the boundary of we have reached outside the boundary of the grid. Okay, we simply return, what do we return? 1. This is base case. Okay, now for this one, okay, what move we have made here? We have decremented the row, we have made an upward move. So over here, if I decrement the row by 1, I go to 0, 0 and 0. Okay, I have made all my moves are exhausted, so we get back to the same state that we started with. Okay, so since all the moves have exhausted, we don't do anything. So this is another important condition to keep in mind. Now what is the next move? What I can do is I can decrement the column. Currently, if I am at column number 0, what will be the decrement? If I'm over here, what will be the decrement in column? It will take me to this place. So I'll say the row number remains same, -1, all the moves have exhausted. I mean, I've been left with no moves, so the ball comes out over here. Okay, this is another base case, this will return 1. Okay, now how many? Okay, one more state is left. Okay, now what will be this one? Since we are moving, okay, so these were 1, 2. Did I miss any state by any chance? Okay, did I? This is one row incremented, one row decremented to the left. Okay, I forgot to increment the column over here. So let's say if the row number is 0, column becomes 1 and the number of moves becomes 1. So we come to this place, right? We come over here. Okay, this move was remaining, so let me just do it one over here. So let's say if I move to the right, what will happen? Currently I'm here, I move one column to the right, so the call will be made for row will be same, column number will be 1 and the moves 0. Okay, so the ball reaches to this place, 1, 2. This will return nothing. right? Because we have exhausted, okay, we are done with all the moves. So this is another condition. So I have shown the recursive tree for one recursive call. Similarly, you can expand this, and this as well. And I hope the tree diagram is clear to you all. Okay, let me just do zoom out, okay, so you can have a clear view of the states. I know this diagram is a little bit messy, but I hope to improve on this, okay? So I hope it gets better and better with the further videos. So I hope I'm clear with the intuition, okay? And even if you know a little bit about recursion, uh, this will make a strong foundation for you to understand it even better, okay? So let's analyze the time complexity, okay? So let's see now what are we actually doing. All right, so initially we have this 0 0 and 2. All right, now we are making 4 recursive calls, okay? One call over here, one call over here, one call, another call, okay? And we are decrementing by 1, okay? So over here I have been left with one move, so I will again make 4 recursive calls over here, okay? I'll make 4 recursive calls, right? Okay, and once I reach these cases, the number of moves will become 0. So this is the termination for all the conditions, right? We cannot go any further because we have been left with no moves. All right, we cannot proceed any further. So as you guys can see, here we are making 4 raised to the power 0 calls. Over here we are making 4 raised to the power 1 call. Over here we are making how many calls? How many calls? Okay. Yeah. So we are making 4 raised to the power 4 calls, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 16 calls. So over here 1 unit of work is being done, over here 4 units, over here 16 units. What do you guys see? This is a geometric progression, right? 4 raised to the power 0 plus 4 raised to the power 1 plus 4 raised to the power 4. How many times? The number of moves that we have, right? So this will lead to an exponential time complexity. Okay, what is all right? So this will lead to an exponential time complexity, right? Okay, what will be the number of levels? Number of levels will be the number of moves we can make, right? Okay, let me just try it once again. It will be number of moves we can make, number of levels. Okay, so I hope I'm clear with the intuition. Let's try and code a recursive solution, and as we move on, I'll advise you to write a complete recursive tree for a smaller test case. Okay, complete recursive tree. Okay, you guys will notice an optimization, that is the states that have been calculated are being repeated. Okay, so make a note guys and improve. All right, so here we are back with another problem, out of boundary paths. Okay, so let me just explain the problem for once, and then we'll understand the intuition behind it and we'll code it up. Okay, so as explained, I'll be coding up the solution once I explain the intuition. So let's see what the question asks us to do. There is a m cross n grid with a ball. The ball is initially at the position start row, start column. You're allowed to move the ball to one of the four adjacent cells in the grid. You can also apply at most max move to the ball. Okay, max moves to the ball. Start the five integers. Okay, we have been given with the five integers that is m, n, max move, start row, and start column. So what is mn? Mn represents the grid area, right? The grid size, m cross n. Okay, max move is the maximum number of moves that we can make, at most, right? At most, the maximum number of moves that we can make to get the ball out of the boundary of the grid, right? And start row and start column are the initial positions of the ball on the grid. Okay, start row and start column are zero based indexed, right? So clearly, if you guys have already solved some of the grid problems, so this is a very famous pattern, right? So if it happened to you, like if you have ever solved any problem that involves grid and graphs in general, then this problem is very easy for you to solve, right? Like you might have solved problems like rotten oranges, or maximum or minimum falling path, something like that. The grid problem that involves to apply DFS at times. So this is one of those problems, and we'll go on to optimize this problem, and we'll see how to optimize it. Okay, and so the intuition that I want you all to know is, see, let's say if the ball is at 0 comma 0, right? What are the possibilities? I can go to the right, I can go up, I can go left, I can go down. So as I can see, as soon as I get to see that there are possibilities, I can choose from paths to take the ball out of the boundary. So from this point only, I can clearly state that the question's approach is going to be recursive. Okay, so let's say if I am at 0 comma 0. So as explained, what I'll do is I'll try to find out the answers from the adjacent cells. If I know the answers of adjacent cells, I know the answer for the current cell. And what is the principle of recursion? Solve one case, rest recursion will handle. As explained in the dry run, not in the dry run, the intuition video, I clearly explained that if I want to find out the answer for the current cell, I will have to find out the answer for the adjacent cells. And if I know the answer for the adjacent cells, I might add up all these answers and return for once. Okay, so what I was saying that if I want to find the answer for the current cell, I need to find out the answer for the remaining adjacent 4 cells. If I have the answer for the remaining 4 cells, I can add it up and return it for the current cell. And this gives me an intuition that recursion will be involved, because I have to take decisions. I can either go up, I can go left, I can go right, I can go down. Okay, and you know how recursion works, right? You solve for one case and rest recursion handles itself, right? That is just to teach someone, like who has a fear for recursion, to just assume that recursion will calculate everything. But I've already explained how the code is working, so let's jump and code it up, right? Okay, so we'll call a helper function. Okay, and we'll pass on the variables. Okay, now what will change? The start row, start column, and the number of moves that we can make will change. Okay, and m and n is going to be same for all time, right? So we'll pass start row, start column. Okay, we'll pass max move, and we'll pass what we will pass. We'll pass start column, sorry, start row and start column, sorry, column. All right, now so let's see. Okay, int helper, I have the row, I have the column, I have the moves. Okay, Okay, what have I done here? Sorry, I have made a mistake, I guess so. This should be here, and over here it should be M, and it should be N. Sorry guys. Temp int N. Okay, so I hope we are together. Start row, start column, max move. Okay, so uh, what will be the base case? The base case will be, let's say if row becomes greater than equal to M, or column becomes greater than equal to N, or row becomes less than 0, or one more possibility, column becomes less than 0. What do? We simply return 1. Okay, because if the cell is already outside the boundaries of the grid, we can return 1, right? Okay, now actually the ball will not be placed outside the boundary. From a particular cell we will come out of the boundary of the grid. Okay, so that is the case when this condition will be executed. Now what do? We have to move in all 4 directions, right? So let's initialize our answer variable that will store the answer. Okay, and this is something that I generally follow in all my grid solving questions. I try to create an array for traversing the rows and columns. So I'll just do it, and I'll explain like what this code is doing later. Okay, 0, 1, -1 and 0. Okay, now I'll loop through I equals 0, I less than 4, I plus plus. Okay, and what I'll say, I'll find out new row, that the new row will be the row that we are going to move in, right? So it is going to be row plus dr of I, and new column is equal to column plus dc of I. Okay, and let's say if the number of moves that we can make is greater than 0, that means we can make a move. So if I can make a move, I'll say answer is equal to answer plus helper new row, new column, and moves -1, just because I made a move. M and N will be same all this time. Okay, so what do? We simply return answer. Okay, let's try and run this code. Okay, so we have got a time limit exceeded error. Let me just reset the test cases. I was actually doing some tests. So how do I reset? Yeah, so I reset the test cases. Now let's see. Okay, so it works fine, right? Now let's try and analyze the complexity. Also, they have also mentioned that we have to return the answer in modulo. So let's handle this case first. Okay, because for the bigger values the possibilities will go out of the ranges of the integer. Okay, so int mod is equal to 1e9 plus 7, and okay, so we are doing addition over here, so we'll just simply say mod. Okay, now I'll take some time to explain the complexity. Now see, what are we doing actually? At each call we are making 4 recursive calls. Okay, let's assume that we are making 4 recursive calls if the moves is greater than 0. So what will happen? Say we have to take 3 moves, right? We have to take 3 moves. So for first move we will make 4 recursive calls, then all those calls will again make 4 recursive calls. Okay, so at first step I make 4 raised to the power 1 recursive call. Then in the next, I make 4 raised to the power 4 recursive calls. And this goes on, right? This will lead to an exponential time complexity. Okay. So we need to optimize it. So what do? We apply DP. And also I'll suggest you to make a recursive tree for a small test case, say for this one, and you guys will notice there are repeating states, and once there are repeating states we can make a cache and we can store the answer, right? We can use a cache memory to store the answer. So let's create one for us for this question, right? Int arr, I'll initialize it with 51. And what is the maximum number of moves that we can make? We can make a maximum of 50. So let's initialize it with 51. So this is going to be, let's initialize the array with -1, memset arr -1 size of arr. Okay, so this will initialize each and every block of our array, 3-dimensional array, to -1. Now what will be the base case? The base case, not the base case, the additional check. Let's say if we have already evaluated a particular state, what do? We simply return the answer, return arr of row column moves. That's it. And let's store the answer in arr row column moves. Okay, is that fine? Okay, let's run this code. All right, let's try and submit this. Works fine. So let me just explain once again what all we have done over here. We have initialized this mod variable that we are going to use. This is the DP array that we have created, and this is the helper function that we are calling. What is the intuition behind this helper function? We can see that we have to make 4 moves, right? We have to go in 4 directions. Let's say if I have the answer, if I want to find out the answer for the current cell, I'll assume that I have the answer for the 4 adjacent cells. And if I have the answer for the 4 adjacent cells, what can I do? I can add them up. I can add the answers, right, to find the answer for the current cell, right? So this is what I have done. So to save my time and write, this answer for 4 different, this helper function for 4 different calls, I've shortened the code and I have written a loop that will go on to explore possibilities in all 4 directions. So what are we doing here? Let's say this -1 represents a decrement in row and the column number remains same. So look at this. Okay, what does -1 and 0 mean? Let's say if the ball is over here, dr means decrement in row is -1. So if current row is 0, row plus -1 will take it to this place. Okay, so it will become -1. So -1 means the above boundary, and column numbers remain same. So we don't move this way, we just move this way. Okay, let me just explain the second one. That is, if the row remains same and column increments by 1. So this is 0, and if it is incremented by 1, we reach to column number 1. So this ball will make a move here. Okay, let me just explain the third one. 0 and -1. So row number remains 0, columns decrements by 1. Okay, it becomes -1. So we have reached out again. Okay, and the fourth one makes this call, that row increases, column number remains same. I hope I'm clear. And in that way we are exploring all the 4 possibilities. We are assuming that we have this answer over here, okay, with moves -1, definitely, because we have already made a move, right? All right, so this is it, and we have applied DP, and we can submit